Hello, everyone, and welcome to our live session for Thursday, November 11th. We are excited to have you all here. There's big astronomy goings on lately, and we are excited. There's things that have just happened. There are things that are happening soon, and we're excited to talk to you about them. Chris, why don't you welcome everyone, and then we'll get started with questions.
Okay, welcome everyone to the live session for people in our online classes or anyone else who happens upon this broadcast, and we're going to open the floor for your questions right now.
Excellent. The very first question is from an email from Anamaya Gayundar asks, what is the difference between an asterism and a constellation?
Good question. An asterism is just a particular grouping of stars, that is notable or memorable or that are in close proximity. So an example of that would be the Pleiades, which is nicknamed the Seven Sisters because the brightest 7 stars are visible to the naked eye. That Pleiades is not actually a constellation. Constellations are historically defined. Their original designation goes back into history because many constellations were noted first by people literally thousands of years ago in Greek, Roman times, and even before. The modern constellations date back about a century when the International Astronomical Union and the astronomers got together and sort of codified or rationalized the constellations, and there are 110 constellations in the northern and southern skies. It originally was 88 and they increased that number. So it's 110 constellations, and those are historically defined patterns that just carve up the sky north and south. Whereas an asterism is just a particular grouping of objects that has no relation to historical constellations.
Excellent. So the next topic that I really want to cover, and hopefully we will get some additional questions about this, is can you quickly talk about what the Astronomy Decadal Survey is? Why, because it just came out recently. Can you talk a little bit about what it is and why it's important for astronomy? And if folks who are watching, if you don't know what the Decadal Survey is, you should go check it out and come back and ask us some questions about that. We'll cover a few topics. But Chris, can you talk about what that is and why it's important?
Right. Let me treat this as several separate questions. First, what is the Decadal Survey? Decadal Survey is, as the name implies, an exercise that's done in astronomy every 10 years where astronomers as an entire professional community come together to define their research priorities. And these are particularly research priorities that need federal funding, so it affects what the national agencies like NASA and the NSF will provide for astronomy. Those agencies are strongly guided by this process because it happens under the auspices of the National Academy of Sciences, and it's led by an overall or an overarching committee of very esteemed astronomers from around the country. And then there's a set of sub-panels or subcommittees working on pieces of the report, and that total number ends up at being more than 300, and many others are consulted, and I think there were over 800 white papers submitted. So it's a major priority setting exercise of astronomers for the subsequent decade. I think it was started by astronomers in the 1960s. We've been doing it for a long time, and other fields have now copied this. Planetary science or space science has its Decadal Survey, and even some of the life sciences have Decadal Surveys now.
Excellent. So as we, have other people weigh in on this, can you talk about what some of those priorities ended up being? Can you because I remember hearing that there are some really important projects that either finally got their sort of prime, like their due prime location. Can you talk about what some of those priorities are for this round?
Sure. And I'll sort of answer a separate question ahead of that, which is what are the pros and cons of a decadal survey, of doing that at all, because there are actually some downsides. It's not all positive. The pro is, of course, that it's very helpful to legislators, to funders, federal agencies, and the entire community for astronomers to get together and agree on priorities for a subsequent period of time. Astronomy is a modest enough size community. Number of professional astronomers is maybe 10, 12,000 in the US, and double that number worldwide. For the US astronomers to come together is possible because there's a finite number of them. I don't know if 150,000 professional chemists might ever agree on anything. So that's the pro, that everyone gets together and it's in a finite period of time and it's prescriptive or very strongly guiding of investment over the following decade. There's downside. The downside is it's sometimes hard to agree and compromises and trade-offs get made, people's feelings get hurt, projects get missed out, and because you can't recommend doing everything because it's supposed to be a realistic budget setting exercise. Another downside, which has really played strongly into the last few decadal surveys, is that the extended timelines of funding things and the delays sometimes mean that a top priority from one decadal survey is not launched or even necessarily completed by the time of the following decadal survey. So you have a tough choice. Do you just assume that it'll get funded and completed, or do you reinitiate or retool that project in a subsequent decadal survey, which moves other things off the agenda? So the whole thing can get backed up by delay. A good example of this is the James Webb Space Telescope, which is a decade behind schedule and billions of dollars over budget, and it kind of busts the whole process because it was presumed to have been launched during the previous decadal survey, and instead it's just launching as this decadal survey drops. So to answer the question of what this new decadal survey prioritized, I can't give the full story because it's quite a long report. It's hundreds of pages, I think 500 pages for the full report. The committee was chaired by Fiona Harrison, a professor at Caltech, and our very own Rob Kennicott, who's a joint professor both at in the Department of Astronomy, one of my colleagues, and also at Texas A&M University. And they were the co-chairs. The key priorities that are of interest to ground-based astronomers were, of course, that the United States should build 2 major new optical telescopes. So the recommendation is that the government should support the funding of both the GMT, the Giant Magellan Telescope, that we are leading the development of with the mirrors that we build in the Mirror Lab, to be built in Chile, and the TMT, the 30-meter telescope being built by Caltech and the University of California, supposedly on a site in Hawaii, but that is controversial and that's not resolved yet. There was a sense that the U.S. would fall behind in world optical astronomy because Europeans have very advanced plans and a lot of funding for their telescope, which is bigger than either the TMT or the GMT. So this was a possibility of just getting left behind. So that's a huge priority, and of course it's a huge plus and a benefit locally here because it almost guarantees that our big telescope will be completed with private funding and federal funding. Another thing that the committee recommended is a modern upgrade of radio observatories and interferometers. The Very Large Array has been around for decades. It's a venerable facility, and radio astronomy has fallen a little behind. Interferometry is an excellent technique and it's been very effective, but radio astronomers have not had a boost to their capabilities recently, and so they are recommending a new capability for a radio interferometer modeled on the VLA, but probably 100 times, maybe 30 times more sensitive. That's another recommendation. Also, X-ray astronomy is recommending a new facility in space. The Chandra Observatory is also quite old, not as old as the Hubble, but it's in its twilight years, and it has limited capabilities in some areas. So the recommendation is for an advanced new X-ray observatory with probably 10 times the capability of the Chandra Observatory. And another priority involves a new large optical telescope. Remember, the James Webb Space Telescope is optimized for the near infrared. It's not really an optical telescope per se, and it can't actually work at ultraviolet wavelengths at all, which HST was very good at. So there's a recommendation for a larger than HST space-based telescope, 6 to 8 meters potentially. The problem with that is the development path for that is slow, and it's probably not going to be built until the early 2040s. So it's a mixed bag, and there's smaller things too. Not all big projects. There are recommendations for smaller projects. And on the side of the workforce and the profession, there's always a chapter about the state of the profession. There are quite interesting and good recommendations about how to increase gender and racial equity in astronomy, how to improve the balance in those regards of the faculty and the researchers doing this, and how to encourage more graduate students to stay in the field because there's a lot of attrition at the moment.
Excellent, thank you. So we're going to switch to a specific astronomy topic again. One of our participants would like to know if there is a calculation that can compare the number of galaxies coming into view due to distance from um, the expansion of the universe, from the Big Bang, with galaxies receding from us due to the expansion of space-time. So, like, is there some ratio with galaxies that are coming into view versus those that are leaving? And what does that look like?
There's a complex calculation. I mean, it's a good question, but it does not have a simple answer because you actually have to plug in the numbers for the entire expansion history of the universe, which had a decelerating phase due to dark matter, and in the last 5 billion years an accelerating phase. Because of the decelerating phase, there are galaxies at look-back times of 7 to 10 billion light years that are actually coming into view. So the observable universe is growing in that regard. However, because of the accelerating expansion, there are also galaxies that are disappearing from view because they eventually will be drawn or moving away from us at faster than the speed of light. I think at the moment that balance is that the observable universe is getting bigger, and so there are more galaxies coming into view. Because dark energy has only dominated the expansion for the last third of the history of the universe. But if we play this out into the future, where dark energy will dominate and actually become an even more dominant feature of the expansion history, because dark matter, remember, is diluting as the universe gets larger, whereas dark energy is fixed in a volume of space, so its power stays the same. That means that dark energy will dominate and that eventually the number of observable galaxies will decline, and eventually quite rapidly.
World of Science, who's on with us live, would like to know about if you can talk a little bit about the recent experiment that has been touted as linking the quantum world with gravity. There was a scientist who was shooting a laser through strontium atoms and has been able to somehow experimentally make a connection between relativity and quantum mechanics. Can you talk a little bit about that effort and if this new experiment shows us anything new?
Yeah, I'm going to have to pass on that one. That's a research project I'm not familiar with. I'll have to look that one up and do it next week.
Okay, sounds good. One of the next questions from one of our live viewers is, do you agree with the idea, or what is your opinion on the idea that gravity is such a weak force because it is spread among extra dimensions?
It's an interesting idea. So the weakness of gravity, by far the weakest of the four fundamental forces, is noteworthy. And the people who are trying to unify the four forces try to make an argument that the weakness of gravity is indeed an indication of a sort of multidimensional super theory, if you like, a theory of everything, where the gravity force becomes diluted, if you like, by those extra dimensions in the way we observe it. So it's an interesting hypothesis. It's not really a hypothesis formed from a fully fledged and currently testable theory, so I just call it speculation at this point. But various people like Lisa Randall, researchers like Lisa Randall at Harvard and others are strongly investigating this, and they're trying to come up with observations that would test this. Those observations that might test this are interesting because they actually involve laboratory experiments, not astrophysical experiments, laboratory experiments that somehow test the incredibly weak force of gravity and how it operates on the level of a lab bench or meter scales. Obviously extremely precise experiments required, and some of these are being constructed now.
Excellent, thank you very much. The next question from one of our live participants is from, sorry, I just lost my place here. Juan Carlos Olmedo asks, can you talk a little bit about alternatives to carbon and even other than silicon to form life? I mean, are there any other ideas about, about life forms that could exist? We've talked about non-carbon, but non-carbon, non-silicon. What are the options here?
So if we're talking about strange life or bizarre forms of life that are not identical to our form of life, then you can go mildly weird or extremely weird. Mildly weird would be to deviate from carbon. Silicon obviously is in the same column of the periodic table, so it shares some electrochemical properties with carbon. However, chemists have now looked at silicon in quite a lot of detail with simulations and actually lab experiments. And while silicon is able to form compounds, complex compounds, it does not have the robustness and versatility and diversity of forming compounds and strong bonds that carbon does. Carbon is preeminent in the periodic table, and it's an abundant element. So the best thinking is that silicon chemistry is an alternative for carbon biochemistry. It might happen, it's possible, but it's not really that viable, and in the end, if carbon is available, then carbon is what will happen, because it's there too, and it's more sturdy, and it's easier to make long-lived, stable, very big molecules, infinite size in principle. So that's what the thinking about silicon is. And elsewhere, in terms of biochemistry formed from chemicals and chemical bonds, there's really no other alternatives. There's no idea of a kind of chemistry that could form without carbon at all, for example, because you have to deal with what nature gives you. And the most abundant elements, apart from hydrogen and helium, which you can't do chemistry with, are carbon, nitrogen, and oxygen, and then silicon, magnesium, sodium, and so on. And there's no other options there. For very weird forms of life, of course, you're deviating from biochemistry completely. You're talking about the idea of perhaps a electrical network that somehow stores codes and progresses and transmits information, or maybe a chemical network that is based on containers that are not cells, and where your chemical reactions occur in a sort of different way, in concentrated forms, in a pore space of a rock, for example. So there are other architectures for life that are definitely weird, but in the end, people expect that carbon biochemistry will really be universal.
Ramani Ranganathan would like to know if you could elaborate a little bit more on the initial moments of the Big Bang and inflation. Can you just walk us through like some of the first steps in that early process?
Well, the Big Bang theory runs out of steam, if you like, or reaches its limit with an era called the Planck era, and that's 10 to the minus 43 seconds in principle. It's a very hard to imagine number, such a tiny fraction of a second after the Big Bang. And that's the size, that's when the universe was the size of a subatomic particle, and where the temperature was sufficient that all the forces of nature would be melded together into a superforce. We do not have such a theory, and so the Planck era and Planck scale physics is not known to us, and so that's the limit of our knowledge. Moving out from there, the first era that we can talk about sensibly, where we have observational input on it, is the inflationary era. And the inflationary era happens from about 10 to the minus 35 to 10 to the minus 33 seconds after the Big Bang. And it involves something called the inflation field, or the inflaton field, which is essentially a function of vacuum energy. It's sort of evanescent energy states emerging out of the pure vacuum, of which there are many of these possible energy states. And these energy states can drive inflation of the vacuum. They can drive expansion of space-time exponentially, and doubling time very short, of course. And so in this inflationary model, the infant universe expands from a smaller than a subatomic particle to the size of a macroscopic object, maybe tens or hundreds of meters, in a tiny, tiny fraction of a second. Then that expansion stops. The potential energy that's part of that inflationary expansion is dumped back into the universe in the form of energy, and that energy turns into the particle contents of the universe, and then it continues a more sedate expansion, the kind that was described by Edwin Hubble eventually. So that's the thumbnail sketch of the inflationary era, but it's important to know that we don't actually know the force or the causal driver of inflation. There are many ideas, but there's no observational evidence. At the moment, we're stuck just trying to show that inflation or something like it actually happened. We don't have a lot of ideas of the physical causes and mechanisms.
Somebody pointed out on the chat, or is arguing on the chat, that the Big Bang is actually entirely theory, but I think it's not simply, in science we would use the word hypothesis, And and so what are the chances that it's totally wrong? And and what are your arguments, or what are the sort of arguments against somebody who says that it's just a hypothesis or it's only an idea?
Right. The status of the Big Bang, the epistemological status of the Big Bang, its place in the hierarchy of knowledge is an important question, because astronomers have grown comfortable with the Big Bang. The original idea is now 70 years old. The prima facie evidence for it in terms of the helium abundance of the universe, we've known that for 50 years. The microwave background radiation discovered in '64, we've known that for a long time. And so it's had evidence to support it, and everyone's pretty much used to the idea that it explains the universe. But it is still a hypothesis. It's still a theory that's missing some important pieces. Primarily, of course, what caused the Big Bang and what were those physical conditions at the inception of the expansion. We simply can't describe that. We don't have good enough physics theories for that. As to the possibility that the whole idea is wrong, the hot Big Bang idea, which is just that the universe started in a small dense state, that's less likely. There is, to be fair, a small community of astronomers and theorists, some of which have quite high repute in the community, that are questioning it, that think there's something maybe fundamentally wrong about it. And there are flies in the ointment. It's a question of whether there are more than flies in the ointment and there are structural or fundamental flaws. There's an inconsistency between the expansion rate of the universe we measure locally with distance measures in the nearby universe and the expansion rate we infer from observations of the microwave background much earlier in the history of the universe. That disconnect or mismatch is a problem, and it hasn't gone away. But that still is at the level of detail. If you're going to argue that the universe was not smaller, denser, and hotter in the past, then there's a lot of data going against that, really a lot of data. And that data interlocks, it mutually supports, and it paints a picture that's pretty hard to refute. Because remember, when you've got data of this vintage and this many types of observation, an alternative hypothesis has a very high bar to clear. So it's not simply a question of, do you believe the Big Bang hypothesis? Do you think it's correct or it describes nature? It's a question of, if you want to jettison it, what do you have to replace it with? It better be something at least as good and hopefully better. And no one's come up with that. So at the moment, the Big Bang is, king of the hill. But like a, boxing, wrestling champion, whatever, always subject to attack, always subject to scrutiny, and always possibly wrong. That's what we always admit in science.
Excellent. We do have a lot of people interested in sort of Big Bang, expansion of the universe stuff. So let's cover a few of those things. The first thing is that people are asking is, what is outside of the universe? What's it expanding into?
So in the Big Bang expanding model of the universe, there's no necessary construct of an external reality. In other words, the hypothesis does not require to be expanding into anything. Essentially, it's observationally defined. We look out in space, and in every direction we look, we see galaxies moving away from us. And the cosmological principle that says we don't have a special location in time and space posits that if we were located on another galaxy far away in space and time, we would see the same thing. So we're pretty confident that's the case. And that means there's no center to the expansion. It also implies there's no edge, because you could locate yourself very far from our galaxy, maybe even beyond our vision, beyond the places light has been able to reach us in 14 billion years, and see the same thing. So the answer to the question of what's outside is, there doesn't have to be anything outside, and there doesn't have to be an outside. It's not required by the theory or the hypothesis.
All right, and then relatedly, what are your thoughts on another universe existing before the Big Bang ended up in this universe?
So the idea of precursor universes, or states that precede the Big Bang, is of course always possible and always on the table, because we don't know what caused the Big Bang, and we don't know what the initial conditions, the exact initial conditions were. In principle, they're singularity, which is hard to describe physically. And so because we don't have any physics to describe the instant of the origin of the universe, we also can't talk meaningfully about a precursor state. People speculate that if the universe emerged as a quantum fluctuation, for example, from some strange space-time construct that may have been full of quantum fluctuations, then maybe you could have other quantum fluctuations in parallel, and that leads to the multiverse idea. You could also have them serially, which means there may have been precursor universes. But these are not currently testable ideas, so I put them firmly in the realm of speculation.
And it seems to me that that's the case for a lot of the questions that people have about things beyond the observable universe, beyond, outside the universe. I mean, we're speculating now to try and figure out what happened at the beginning of our own universe. So beyond that is sort of even more wild speculation. It seems like, what is their supporting evidence for sort of ideas like that?
Yeah, I mean, the question of what is the limit of the Big Bang model and where does the realm of speculation start? It's an important question. If you have a model that you trust and that you think explains the universe you live in, it's reasonable and in fact expected and part of the scientific method to push it to the limit, to test it, to see if it applies in regimes that you didn't think it applied. And so at the moment we're just in the business of verifying the Big Bang, and we're trying to push back the timeline, especially to the inflationary era and possibly eventually before that. These other questions, though, of precursor states, the Big Bang, parallel universes, the multiverse, these are absolutely in the realm of speculation. So I sometimes have to be a little emphatic about that, because people just think, well, we have a Big Bang, why not have another Big Bang and a precursor Big Bang? And sure, you can say that, but in science you have to say something that emerges out of a physical idea, out of a hypothesis that's based in physical theory, and we don't have such physical theory. We really don't. So it seems kind of awkward and disappointing to push those questions aside and say we can't answer them, but that's sort of the state we're in right now.
The next question is from one of our live participants. Aman would like to know, can you talk a little bit about your views on the simulation argument or simulation hypothesis, and what do you think the odds are that we're in a simulation, and how would we even be able to tell?
The simulation hypothesis has been around for a while, a few decades now, and in simple terms, it supposes that some sufficiently advanced civilization would go further down a road that we're on, the road of creating simulated environments, of reproducing biology in terms of pure computation, and at some point, therefore, you could imagine a computer simulation in the far future, maybe not that far in the future, that would reproduce the history of all the thoughts that every human ever had. And at that point, you could create a simulated civilization, a simulated Earth, a simulated set of people having their thoughts, living their lives, and it would all be part of a computer. That's the simulation hypothesis. And the challenge is, how can you disprove this hypothesis? At one level, it's hard to disprove, because if you've posited it's a perfect software, it has no glitches, like the famous glitches in the Matrix movies, you wouldn't be able to discern it. It would be indistinguishable from reality, so how would you know? So in that sense, it's a kind of sterile hypothesis, because it almost suggests that you can't test it. And therefore, the question of what are the probability that you live in a simulation is also a slightly meaningless question, because you can't test that probability anyway, so you could pick any number you want. Nick Bostrom, who's one of the architects of the simulation hypothesis, he puts that number quite high. I think he's variously said 10% or 30% probability that we live in a simulation. But there are other people, philosophers particularly, who are skeptical about some of the arguments in the simulation hypothesis, who've said that the probability a priori should be extremely low, because it's essentially on its face a pretty outrageous hypothesis.
Excellent. So another exciting moment for astronomy is coming up in the next month, or a little bit longer than a month. And that's the launch of the James Webb Space Telescope. Can you talk a little bit about that telescope and why it's exciting for the astronomy community?
Sure. James Webb, when it launches, will be a sigh of relief, because it's been a long time coming. It won't be the final sigh of relief, however. James Webb has to get to a Lagrange point that's 1 million miles from the Earth and successfully deploy its 18 hexagonal segment mirrors that are folded as it launches, because it's a big telescope, 6.5 meters, it only fits into the spacecraft folded up, and it has to unfurl its solar panels. There are apparently, in recent articles, there's claimed there are about 300 potential failure modes based on the number of moving parts in the deployment of James Webb. So just launching it without the rocket blowing up is only the first part of the story. Deploying it at its eventual location is going to take a while, probably several weeks, and then the scientific shakedown phase, I think, is as much as 6 months before it actually starts doing science. It's long awaited. It's been called, in a famous Nature article about 10 years ago, the telescope that ate astronomy, because its budget has ballooned from an initial under $1 billion to over $10 billion, and that's obviously stopped some other projects from being built during this time. And it's on about a 10-year overrun in time as well, so it's usurped a lot of other priorities in astronomy. It's in the too big to fail category because astronomy has put a lot of eggs in the James Webb basket, and so everyone is fervently hoping that it will work.
On that, excuse me, on that note, are there, Lorento would like to know, is there any plan B in case there's some sort of, I mean, obviously if it explodes on the launch pad or during launch, there's no plan B. But if there is a failure somewhere along in the mission, do you know if there are backup plans?
It's tricky. So there's no clear plan B for James Webb. There's no second telescope. There are occasionally space missions where there's a backup, where they duplicate a lot of the hardware and they could make a copy of it. This project is so complicated and expensive that there's no second version of the James Webb. So if it blows up on the launch pad or trying to get out of Earth's orbit, then that's too bad. Also, it's in an unserviceable location. The Hubble Space Telescope, venerable as it is, over 30 years and counting, and a very small telescope really by world standards, not in the top 70, I think, of the largest mirrors of professional astronomers, has been cutting edge because 5 times astronauts serviced it. That won't happen again. But each time their instruments were rejuvenated, or if there was a problem, as it was happening with the gyroscopes, for example, they could be replaced. Well, James Webb is unserviceable. Astronauts are never going to go to that location. It was never planned, and so it essentially has to work. Now, if there are certain types of hardware failures, NASA engineers and spacecraft scientists are pretty resourceful, so there have been satellites and space missions where there's been failures when the satellite was far from the Earth, and they've done workarounds, reprogrammed, they've mechanically jiggled or moved or accessed things in a different way, and they've recovered the situation. So there's some level of that's possible with the James Webb, but not really. It pretty much has to work the way it is, straight out of the box.
The next question is again from one of our live participants who would like to know how the James Webb Telescope will assist astronomers going forward now and then long term in the future.
James Webb is designed to have at least a 10-year working lifetime, and obviously people hope for a lot longer than that. Hubble was probably only destined for 10 years, but is now 31 and counting. So the hope is James Webb will be doing its work for at least a decade and hopefully a lot longer. Astronomers are doing general purpose science with it. It's not a single purpose telescope. It is mostly filled with infrared instruments. There's infrared spectra, there's infrared spectroscopy and imaging, there's near infrared and mid infrared capabilities going way out into the thermal infrared, but it's looking at all manner of astronomical targets. The killer app, if you like, for James Webb was always first light, seeing the earliest galaxies in the universe, whose light is redshifted so much, a factor of 10, that is moved into the near infrared, and you actually have to observe them that way. Hubble can't find such galaxies. Too small a telescope and working at the wrong wavelengths. James Webb is also going to be able to do spectroscopy that will diagnose the atmospheres of exoplanets, Earth-like or super-Earth-like planets, looking for telltale signatures of life in the atmospheres of those planets. That's a very exciting use of James Webb. Those are probably the top 2 applications. But James Webb is also going to provide new information on black holes and supernovae, uh, see deep into star forming regions to understand the actual mechanisms by which stars form. It's going to do foundational astrophysics in almost every field.
The next question is from Vincent, who sent an email. What is the current thinking on the major types and relative frequencies of exoplanets?
Well, it's evolving. As we hit 4,000 and counting, heading towards 5,000 exoplanets known, the categories of exoplanets are becoming better determined. In the early phase of exoplanet discovery, you couldn't really judge what the true population was because astronomers were always going to be biased towards finding exoplanets that were more massive and on closer orbits to their stars. So that's why hot Jupiters emerged as an early category of exoplanets. And there was a time when less than 100 or a few dozen had been found when a lot of them were hot Jupiters. But we now know that hot Jupiters are less than 10% of the population. So I think only now, with this level of research and with over 25 years of data, are we beginning to say what the true populations are. And the way it looks is that Earth-like planets or super-Earths are the dominant category. In fact, there are more super-Earths that are objects that are 2 to 4 times the mass or the size of the Earth than there are Earth-like planets. So super-Earths are an abundant category, and I think the next most abundant category is mini-Neptunes or Neptunes. Jupiters and true Earth-sized planets or smaller are the smaller categories. So that means that's an interesting conclusion already because we don't have any mini-Neptunes or super-Earths in our solar system. So that sort of implies, relative to overall statistics, that our solar system is a little unusual.
Thank you. The next question is from Mickey, who asks, what do you hope for from the Lucy mission to Jupiter's Trojan asteroids?
Right. The Lucy mission is an exciting mission that is on its way, and it's a long route because it actually comes back as the nature of these missions. To get to the outer solar system, you need energy, and you can't do it all in rocket fuel because you can't carry that much rocket fuel. So you use gravitational assist. So the Lucy mission is actually going to make 2 ventures back into the inner solar system near the Earth to use gravity assist to boost its orbit to get to both the regions of the Trojan satellites of Jupiter. The Trojans are groupings of objects that orbit 60 degrees ahead of and 60 degrees behind Jupiter in its orbit. That's a stable gravitational configuration. And these are obviously planetesimals. They are small objects that are the kind that probably went into making giant planets early in the history of the solar system. But they've been unaltered since then. So it's another way of astronomers looking at pristine material dating back to 4.5 billion years ago when the solar system formed to really understand how the giant planets formed.
Excellent. And then for those of you who have heard, there was a glitch with the opening of the one of the solar panel arrays on that mission. And I just looked it up, and it sounds like they're going to try and possibly redeploy it, but they won't be able to do that till after November 16th. So that seems like the earliest. Have you heard any other updates on that, Chris?
No, I haven't heard anything on that, no.
Okay, excellent. The next question is from a Faisal who asks, how do scientists currently determine the age of the universe to be 13.8 billion years?
The age of the universe is interesting because it's actually measured through a model, through the expanding universe model in the Big Bang theory. It's not that we measure an exact age in the way you might measure the age of a star through a stellar evolution model. So we actually measure the expansion history of the universe by looking out in space and back in time, and we can therefore project the universe to 0 size in a Big Bang model, and that becomes the age of the universe. So the age precision depends on the accuracy with which we can measure the constituents of the universe, which are normal matter, about 4%, dark matter, about 24%, and dark energy, the rest. Those are measured fairly accurately to about 1%, and therefore our measure of the age through the Big Bang model is accurate to about 1%. So it's a fairly accurate age. But it is derived from a model, and so it does depend on those other measurements. There's no direct measurement of the age. There are cross-checks, however, on the age. And one of those cross-checks is looking at the oldest stars we can find in our own galaxy. Clearly, it would refute the Big Bang model and the Big Bang age if we found a star that was older than the age from the Big Bang model. And we haven't done that. The oldest stars we can find are around 13 billion years. So that's a check mark against the Big Bang determined age. There's also a less accurate but completely independent method, which is called nucleocosmochronology, and that's the use of radioactive isotopes in the solar system and the nearby universe to infer the age of the universe from how those isotopes have evolved. These are very long-lived isotopes with half-lives of billions of years, similar to the age of the universe, that let us indirectly measure the age from the way they've decayed. But it's based on pure physics. The uncertainty is significant, maybe 10 or 20%, but also those isotopes, radioactive isotopes, agree with the Big Bang age. So there's a fair amount of confidence that the age really is 13.8 billion years.
Finn McCool asks, or states, that they're working on a course which said that the universe is expanding faster and faster, but yesterday read that scientists are no longer sure that this is the case, and maybe it's measurement errors. Can you talk about the current state of the expansion? Are we moving into this acceleration phase, or is that now in question?
I don't think the issue of the acceleration is in question. The measurements are difficult and still uncertain. The detection or the measurement of dark energy, a discovery from 1995 and 1996, the accelerating universe, it won a Nobel Prize, that discovery, a few years ago. That's fairly robust. There's no question that the universe is accelerating, and it started accelerating about 5 billion years ago. So there's nothing in recent data that refutes that. There is, of course, a lot of data still needed to understand the nature of the dark energy that drives this accelerating expansion, and we really don't have that information yet. So dark energy is a cipher. We simply don't understand what it is physically.
The next question from one of our live participants is, does gravity have speed?
Well, in the standard model of particle physics, which analogizes gravity with the other fundamental forces, electromagnetic force has the photon as the carrier of that force. The strong nuclear force in the atomic nucleus has the gluon as a carrier of the nuclear force. The weak force that's responsible for radioactivity has the W and Z particles as carrier of the force. So by analogy, gravity in that model has a graviton as a carrier of the force. It's a spin 2 particle in that standard model, and it would propagate or travel at the speed of light, propagating gravity at that speed. However, direct experiments to measure the propagation of gravity or to detect a graviton have not succeeded. Detecting a graviton is probably not possible with current technology. But even an experiment to infer the speed of gravity propagating is tricky, because if you think about it, you have to switch gravity on and off to make an experiment like that. And that's not really possible for us either with current technology. So there's no affirmation of this analogizing idea that there's a graviton that carries the gravity force at the speed of light.
So the next question is about some of the priorities in the Decadal Survey. So the question is, what will the new large telescopes, these super large telescopes that are being recommended to be built, capable of doing that is different than, for example, space telescopes? And what's your opinion on building future ground-based observatories versus trying to pour money into space-based telescopes?
So there's a couple of things to be said about the trade-off between ground and space-based telescopes. First, per unit area of telescope mirror, it costs roughly 10 times as much to put a telescope in space as to have it on the ground. And that's why we have much bigger telescopes on the ground than we do in space. Hubble Space Telescope is a 2.4 meter mirror, and in Arizona, we have the LBT, which is equivalent to an 11.8 meter telescope on the ground. Much, much bigger, light gathering power 20, 30 times more. And that will be true in the future too. So for more light gathering power, you have to stay on the ground. The other thing that's happened that some people are not aware of, is that adaptive optics has matured to the point where we can use this technology to cheat the atmosphere, if you like, and recover the diffraction limit of a large telescope, and essentially reproduce the image quality you get in Earth orbit from the Hubble Space Telescope. With our Magellan telescope in Chile, a research group achieved images that were sharper than the Hubble Space Telescope a few years ago. With the giant Magellan telescope under construction in Chile, we'll have 10 times the angular or spatial resolution of the Hubble Space Telescope. So now you can do better in that regard from the ground. And so the question sort of turns on its head and becomes, why would you do space telescopes at all when you can get sharper images from the ground and have much larger mirrors and the cost is lower? And the answer to that is that not all wavelengths of light get through the Earth's atmosphere. James Webb is working at near-infrared wavelengths for the most part, where the Earth's atmosphere is muddy or partially opaque, and so it will do much better. Also at thermal infrared wavelengths, the background matters, and so you need to be in a cold environment. The Earth is a warm environment, and so there's a lot of infrared background, and the backgrounds in space are hundreds of times lower, so you'll always do better in the infrared from space than on Earth, dramatically so. And then of course for ultraviolet or X-ray or gamma ray, you have to go into space anyway because the Earth's atmosphere is opaque to those wavelengths.
So then a follow-up to that is, how many more telescopes do you think we can realistically build on Earth? Are we running out of spaces to put large telescopes? There seems to be plenty of opportunities in places like Chile, but with so much pushback in places like Hawaii. How much longer do you think we can still build large telescopes ground-based?
It's a good question. In terms of the best observing sites, yes, the number of premier observing sites that it's worth spending billions of dollars and a generational project to put a telescope on a mountaintop, those are a limited number of locations. And Chile pretty much has a lock on those locations, whether it's in the northern Atacama with the ALMA array up at 4,000 meters elevation, or the more modest elevations of the middle latitudes of Chile where the giant Magellan telescope will be built, and the large synoptic survey telescope too. So Chile has a lock on the best sites for observing. Hawaii is controversial for understandable reasons associated with the native Hawaiian sacred mountain of Mauna Kea. The next best sites are actually not that good, and they're harder to get to because Chile has great infrastructure for doing astronomy. So in a sense, we are running into the limit of where the best sites for big telescopes are. And you don't really want to put all your telescopes in one country because, as we realize with these new large telescopes, you need to cover the northern hemisphere as well as the south. So you can't put everything in Chile. You need some northern hemisphere sites. In terms of how many more telescopes can really be built, the other issue and limitation is really resources. These telescopes are extremely expensive. The giant Magellan telescope and the 30-meter telescope will each cost $2 to $3 billion. And there's simply not enough money in the federal budget or even in private hands to do that more than once in a while. And the Europeans will be fully maxed out by their 38, 39-meter telescope they're planning. So there's a real question in the community as to whether there will ever be a generation beyond this because of the resource cost of these telescopes. And then the other thing is engineering. It actually starts to get very hard to engineer a telescope of 50 or 100 meters and give it the accuracy of pointing and the image quality that we expect with our telescopes.
So then is it worth it to build more like 10-meter class telescopes since they're more cost effective, or do we have enough of those? Is it really only worth putting money into the absolute largest facilities?
In terms of the mix of facilities, this is something the Decadal surveys worry a lot about. They don't want to create a situation where all they recommend is huge, frontier, exciting, cutting-edge facilities. It's easy to make a case for those, of course, but if that's all you had in your portfolio, it would not serve the whole community. So the Decadal survey, this time and in previous decades, has always recommended a mixture of small, medium, and large facilities. And the small facilities are cheap. And the technology for building 1, 2, 3-meter telescopes is really mature. Amateur astronomers have 1-meter plus telescopes now, and more than occasionally. So yes, there's resources that can be put into those telescopes. At some point, of course, you run into a different limitation, which is we're already saturated in data. Astronomers can barely dig out of the data they have now, given current facilities and the CCDs, which really gather enormous amounts of data. Large Synoptic Survey Telescope will be 20 terabytes a night, for example. So with these data volumes and the facilities on the horizon, there's a serious concern that we won't be able to keep up with the science, or there won't be enough astronomers to do the work. Because the other issue, of course, is the workforce, the profession, and how many astronomers you're training, how many astronomers the country or the world can support and give jobs to, and that's now becoming a serious issue.
All right, moving on from the topic of telescopes, Art Studio asks, why is the transit method so successful for discovering exoplanets?
The transit method is the preeminent method for exoplanet discovery. The first 100 or so, 150 exoplanets were found with the Doppler method, and that's how the Nobel Prize winning discovery of 51 PEG was done in 1995. But the transit method then took over, and it took over dramatically with the launch of the Kepler telescope. The reason the transit method took over is because its sensitivity is so great. It's fairly easy, and it was shown to be easy by Kepler early on, to detect a transit that's 1/100%. That is a dip in the brightness of a star temporarily that's 1 part in 10,000. And that corresponds to an Earth transiting a sun-like star. Well, with that sensitivity, it's easy to detect Earths if they're out there. The only caveat is that you can only see particular orientations. So you have to observe tens or hundreds of thousands of stars to find the few, not that have Earths, but the few that have Earths and are in the right orientation such that the planet transits. But you can use the fraction of those transits to infer the total population. By contrast, Doppler method starts to run into difficulties trying to go much beyond Earth mass or much below Earth mass. And the reason is that the stars that it's measuring the Doppler shift relative to have atmospheric turbulent motions. And those turbulent motions can be meter per second or so, and so they start to reach the level, the motions in the atmosphere, the churning motions of the sun's atmosphere, reach the level of the signal of an orbiting sub-Earth mass planet. So radial velocity method is essentially running out of steam below an Earth mass, whereas Earth-sized planets with the transit method were shown to be easy to detect a decade ago, and we're still finding most of them that way.
Do you foresee any exoplanet observation methods that could ever beat the transit method, or sort of take over in the number or sensitivity?
The transit method that beats all, but not in terms of yield or number of exoplanets, is microlensing. It's a niche method, and I think microlensing has so far only found a few dozen, maybe 40 or 50 exoplanets out of the thousands that have been discovered. It's an important niche method, however. First of all, what is it? It's caused by the gravitational effect that mass bends light. And so if you have a planet orbiting a star and that star passes in front of another star, the intervening star will cause the background star's light to amplify in a gravitational lensing event. And if that intervening star has a planet associated with it, it'll create a secondary amplification. The sensitivity of that method is such that you can detect easily Earth mass planets, Mars mass planets, Mercury, down to almost moon mass. So it's very sensitive. There are two downsides, however. One downside is that you don't get any other information. These are transit events, it's transient events. It's one star crossing another, and that event will never repeat. So unlike the Doppler or the transit method, which repeat periodically with the orbital period, the microlensing event does not repeat, so you have to gather statistics. And the other limitation is that you don't really measure the distance to the system or any other properties of the system. You just measure its mass, and you're uncertain in the mass because you're uncertain about the distance. But generally, microlensing is the most sensitive method for exoplanet detection.
Excellent. Michael Baker would like to know if you can talk a little bit about the M87 Black Hole image, and if you could kind of explain what's going on there and what's being seen in that image.
The iconic image of the black hole in M87, released as a first major scientific result of the Event Horizon Telescope, is a striking image. Remember, you're seeing a telescope that works at millimeter or submillimeter wavelength, so it's not making an optical picture of the black hole. It's making essentially a radio or submillimeter picture of the black hole. So the color, typically the orange color images you see, is a false color of just representing radio waves. That said, what you're seeing is the bright rim around a dark center, and it's not completely symmetric. The black silhouette is not symmetric. It's not a perfect circle, and the brightness around it is not symmetric at all. It's quite asymmetric. What you're actually seeing, therefore, is the shadowing of the event horizon, and that's the darkness, and then the bright light around it is hot gas in the accretion disk around the black hole, and the asymmetry in that brightness is caused by the fact that the accretion disk is rotating very rapidly, and so there's Doppler boosting of the disk when it's approaching the observer, as opposed to the opposite side of the disk where it's receding from the observer. So there's a lot you can learn from that image, and people have modeled it now. And very recently, in the last year, they were actually able to tease out magnetic field orientations by looking at polarization in the radiation. That's very exciting, because the magnetic field entrained by a black hole also affects its accretion disk. So people have learned a lot from this image, and they've been using it to test the general relativity idea and also to test the way black holes form and evolve.
Excellent. Related to telescopes, Zora would like to know if arrays of telescopes might make more sense than building large telescopes, so building lots of small ones instead of building these massive projects.
So for radio wavelengths, arrays of telescopes absolutely make sense, and most of the excitement in radio astronomy in the last decade or so has been from arrays of radio telescopes rather than single dishes, because those arrays can be combined interferometrically. So the VLA was the original example of this. We've got the very large baseline interferometer, which uses baselines that sometimes span the whole Earth or even beyond into Earth orbit. And then the Event Horizon Telescope more recently, working at millimeter wavelengths. So for radio astronomy, arrays are going to be the way to go. And then the Frontier facility under construction currently in South Africa and Australia is the square kilometer array. For optical telescopes, the same could be true, but the technology is much harder to make work. Optical interferometers do exist. They have been around for a while. There was one developed at Palomar Observatory 30 years ago. There's one in operation at the Keck Observatory in Hawaii. And they are doing science, but it's very difficult, because to make an optical telescope interferometer, which means combining coherently the light from different optical telescopes, which could be individually quite small, you have to maintain the coherence of that light. And the wavelength of light, optical light, of course, is 400 to 500 nanometers, so incredibly small. And maintaining that coherence is a technical challenge that has been mastered but not really scaled up to larger arrays. So at the moment, there are no equivalents of the VLA, say, among optical telescopes just because of those technical challenges. Those challenges are being overcome, but slowly. And so I don't really see optical interferometry being a big component of optical research astronomy in the foreseeable future.
All right, it is 10:59. We have time for one more question, and we will end it. So we'll end this session after that. The final question for today is from Faisal, who asks, who would like to know how about communicating with the James Webb telescope. Is there a chance that the moon could block the signal from Earth and, from the James Webb, since it's so far away? Do we have to worry about interference from other things or from the moon?
So given the moon's orbit and the location where the James Webb will be situated relative to the Earth, moon, and sun, there's no danger that the Earth will occult the signal. In terms of other forms of interference, there are concerns. Actually, the biggest concern, which occurs for all space missions these days, is a solar storm or a solar superstorm, which could interfere with communications across the solar system to all the space probes we have out there. as with all facilities of this scope and magnitude and cost, there's redundancy built into the telemetry, there's redundancy built into the transmitters and the receivers. There's no single point failure mode for getting data back from the James Webb, because that would be the worst outcome of a project that expensive if data transmission, was your fatal flaw, your Achilles heel. So really the way they've designed that with redundancy and multiple modes and multiple wavelengths of telemetry getting back to Earth, and many places it can be received with big dishes on the Earth, I think getting the data back is pretty secure. Thanks for your questions. A lot of good questions today, covering a lot of subject matter, and I think we're with you in a couple of weeks. I think our next session is known, right, Matthew? But I don't know.
That's correct. It's going to be Tuesday, November 23rd will be our next one, and it's going to be an hour later than this one. So it would be starting right now instead of ending right now.
Right. Okay. Thank you. Thanks, Matthew, for facilitating. Thank you all for being online, and we'll be with you in a couple of weeks.